Select the major product or products of the following reaction. So we are starting with a benzene ring that has a methyl group and a chlorine already attached. And the conditions that we're using don't look like our typical, say, electrophilic aromatic substitution reactions. Because what we're reacting this with is a really, really strong base, sodium amide, right? The structure here is really a sodium plus, which is not an electrophile, and the amide anion. So it does not look like we're doing an electrophilic aromatic substitution. We've got a really strong base and a strong nucleophile. So we're not doing electrophilic aromatic substitution, we're doing some nucleophilic substitution instead. And so we have seen previously a couple examples of nucleophilic aromatic substitution reactions where we added our nucleophile and then eliminated a leaving group. So again, we have a leaving group. So this is what's going to be replaced in this. It's just a slightly different mechanism than the reactions that we've seen previously. So in this case, we're going to do elimination and then addition. So elimination and then addition. And so in case you're wondering, well, how do I know what the substitution mechanism is going to be? Remember that your classical SNAR reactions that we saw previously needed powerful electron withdrawing groups that were ortho and para to the leaving group. And we don't have that. We don't have powerful electron withdrawing groups. And so this was the opposite, addition and then elimination. So paying attention to what your substrate is will give you an idea of which mechanism you're going through. So that's just kind of an aside. That's the other nucleophilic aromatic substitution mechanism. Okay, so with this strong base, it's going to undergo elimination and then addition. So the elimination here is going to look much like the elimination that you saw when you looked at, say, E2 reactions, right? So you've got a leaving group, so you're going to take a hydrogen from one of the adjacent carbon atoms. So we can draw one here, and we can take that strong base, strong nucleophile, and do an elimination. But the intermediate we get is really interesting, because when we remove this hydrogen, these electrons have to go somewhere, and where they go is right here to form a triple bond. So we get an interesting intermediate that if you look at it and think, gosh, that doesn't look stable, you're right, it's not. And let's draw it. So we've got the methyl benzene, except that it's no longer benzene. We now have a triple bond. So this intermediate is a substituted benzyne, which is, as you would imagine, very, very reactive. Triple bonds are usually linear where they're sp2 hybridized, so constraining this into the ring is making this extremely reactive. So that's the elimination step, is to form the alkyne, and then the addition is your nucleophile can then add to either side. So we'll just show it adding to one side in terms of our arrows, but I'm going to acknowledge that it could add to either side of the benzyne. And so what that means is it's going to give us a mixture of products. So I'm going to draw an arrow down to here so I have some space to draw the two addition products, either adding the NH2 here or adding it to the other side of that alkyne. All right, so if we moved one pi bond, we still have one there. So we've got an aromatic ring again. We've got the NH2 added, and we've got a lone pair of electrons. And if that had added to the other side, if it added here, we would also get this constitutional isomer. Okay, so we are going to get a mixture of products as we're seeing here in D. And so when you form this anion and you're still in this liquid ammonia solution, that can be the source of your proton. just in case you're wondering where that comes from. So you can protonate. And notice that generates more of the NH2 minus, so you can keep doing reaction with more of your starting material. And we can, I guess, draw that again here for the other constitutional isomer. All right. And then finally, your acid workup isn't going to change the product. This mechanistic step will get you to the product. This is just neutralizing everything in the end.